Usually, when we talk about a diagnostic system, there's this expectation of precision.
Yeah.
Like if you break your arm, an X-ray shows a jagged white line on a black background.
Right. The doctor points to it and you know exactly what's wrong. It's binary.
Exactly. It's clean, visible. But step into the world of human language and that X-ray machine just, well, it completely shatters. You can't just point to the meaning of a sentence the way you point to a fracture.
No, you really can't because language is inherently ambiguous, right? It's contextual.
Which brings us to today's deep dive. If you're a graduate student gearing up for finals, consider this the first part of your course recap. We are synthesizing the foundational concepts of natural language processing, or NLP.
Yeah, we're going to map out how NLP bridges the gap between messy human language and strict computation. It's a massive challenge.
Our mission today is to understand how these systems evolved from rigid, simple word counters into the dynamic architectures running on your phone right now. Systems that converse, listen, and process millions of documents across enterprise servers.
And to do that, we really have to look at the layers of language understanding. It's not just about words.
Right, there's a whole hierarchy. You've got your lexical analysis, which is just looking at the words themselves, then syntactic analysis for grammar.
Semantic analysis for actual meaning, and then you zoom out even further to discourse analysis, how sentences connect, and finally pragmatic analysis, which is the real-world context and intent.
Which is why NLP sits right at this crazy intersection of linguistics, artificial intelligence, machine learning, and scalable computation. And historically, we spent decades trying to brute force this problem.
Oh yeah, the old rule-based systems. We tried handcrafting grammar templates, basically assuming we could map every single possible variation of human speech.
And that failed miserably, right? Because human language is just too chaotic.
Completely. It was incredibly brittle. So the field moved to statistical NLP, which made things data-driven. We started counting word frequencies, using n-grams, bag-of-words models.
And using classical machine learning on top of that, which was better. But looking at your notes, the real pivot seems to happen when we stop just counting words and start using representation learning.
Exactly. We replaced those sparse, symbolic representations with dense vectors. You turn words into mathematical coordinates so the model can actually capture semantic similarity.
But even with dense vectors, there was a massive bottleneck early on. If you wanted a model to analyze, say, movie reviews, you had to build a movie review model from scratch.
Right, and the computationally intensive nature of that approach is just unsustainable. You can't do that for everything.
So what changed? How did we fix that?
The solution which really drove the modern machine learning boom is sequential transfer learning. Instead of building a new brain for every task, you pre-train a massive model on an unlabeled text corpus.
Like just scraping the entire internet.
Yeah, exactly. You teach the model the fundamental structure of language itself, basically unsupervised. Then you take that pre-trained foundation and perform an adaptation phase.
Fine-tuning it on a much smaller, specific data set for whatever your actual task is.
Precisely. And this all relies on language modeling, which is foundational for prediction, translation, text generation, all of it.
Let's dig into how that foundation actually works mathematically, because the evolution of vector semantics is wild. We started with static embeddings, right? Things like word-to-vec and glove.
Yeah, and to understand those, you have to grasp the distributional hypothesis, the idea that words occurring in similar contexts tend to have related meanings.
Meaning is context.
Exactly. So models like word2vec use architectures like CBOW, continuous bag of words, or skipgram to learn these low-dimensional dense vectors.
But I always visualize those older static models like a printed pocket dictionary. The word bank, for example, gets a single fixed mathematical vector.
Right, it's static.
So it doesn't matter if you say, I'm sitting on the riverbank or I'm opening a bank account. The model sees the exact same numeric coordinates.
Which fundamentally crippled a model's ability to, read the room. It doesn't know which bank you mean. And that limitation led to context-based models and eventually the transformer architecture.
Enter BERT, bidirectional encoder representations from transformers.
Yeah.
BERT completely threw out that static dictionary approach, didn't it?
It did. It revolutionized the space.
But looking at the mechanics of BERT in these sources, the way it processes text is totally counterintuitive to how we read. Humans read left to right.
Right.
But BERT uses a masked language model. It seems to, randomly black out words in a sentence, and then looks at the entire surrounding context simultaneously, both left and right.
It's a brilliant training mechanism, honestly. By masking about 15% of the tokens in a sequence, you force the neural network to develop a deep bidirectional understanding of the structure.
So it's processing globally, not sequentially.
Yes, but to do that, you have to format the data meticulously. The model needs structural anchors. You insert a special classification token, the CLS token, at the start.
And a separation token, SEP, between sentences, right?
Exactly. So the architecture understands where thoughts begin and end in that global view.
Okay, but I want to push back on what this model is actually doing. If BERT is looking at the whole sentence, masking words, running massive computations, does it actually know the difference between a river bank and a financial bank?
Well,
Or is it just doing, incredibly advanced pattern matching?
it really depends on how you define knowing. BERT does not have a conceptual human understanding of water or money.
Right. It hasn't been to a river.
Exactly. What it has done is mathematically mapped the distributional semantics so perfectly across billions of parameters that it can differentiate meaning based on contextual weights.
So it dynamically adjusts the vector for bank based on whether water or money is floating nearby in the multidimensional space.
You nailed it. It's all math.
Okay, so we have this mathematical representation of context.
Right.
How do we get it to talk back to us? Because jumping from understanding context to holding a conversation brings us to dialogue systems.
The taxonomy here is crucial for students to remember. You generally have two distinct categories. First, task-oriented systems.
Like virtual assistants trying to achieve a goal, booking a flight, turning on the lights.
Right. And then you have non-task-oriented systems, which are your open domain chatbots designed for, chit-chat and entertainment.
Let's look at those open domain chatbots first. According to the course materials, they learn from massive data sets of human conversations. And they basically spit out responses using two different methods, retrieval or generation.
Correct.
With retrieval, they're basically digging into a database of existing human responses and picking the best one. But how do they make that match? The notes highlight bioencoders as the modern solution here.
Yeah, a bioencoder solves one of the oldest problems in information retrieval, which is vocabulary mismatch.
Give me an example of that.
So if a user asks, where is the nearest medical center? And the database has the response, the hospital is 2 miles away, a simple keyword search fails.
Because the exact words don't match, medical center versus hospital.
Right. So a bioencoder uses two separate transformer networks. It passes the user query through one and a candidate response through the other, projecting both into a dense vector space.
It's turning both sentences into coordinates.
And then it calculates the dot product between those two vectors. The dot product essentially measures the angle between them.
So if the vectors point in the same direction, the semantic meaning aligns, even if the vocabulary is totally different.
Exactly. The chatbot retrieves the response with the highest dot product score.
That makes total sense for retrieval. But what about generation? This is where the model uses an encoder-decoder architecture to generate a response word by word.
Right, it's synthesizing new text.
But if a model is just trained to predict the statistically most likely next word, shouldn't it just generate incredibly boring text? I mean, statistically, the safest response to almost any question is just, I don't know, or I'm okay.
Yeah, you've identified the fundamental flaw of naive generative models using greedy search.
Greedy search.
Yes. Greedy search always picks the single highest probability word at every step. Now, in machine translation, that works because there's usually a strict phrase alignment.
But conversation is open-ended.
Exactly. If you always pick the safest next word in a chat, you end up in a localized trap of repetitive, bland responses. To fix this, engineers replace greedy search with diversity-enhanced beam search.
How does beam search change the math?
Instead of just looking at the single best next word, beam search keeps track of multiple possible sequence paths, or beams, simultaneously.
Oh, I see.
It evaluates the probability of the entire phrase. This allows it to occasionally pick a slightly less probable word early on if it leads to a much more coherent and interesting sentence overall.
Okay, now contrast that open-ended chit-chat with task-based systems. These aren't trying to be interesting. They're trying to get things done. The notes detail a dialogue state architecture for this. It seems to treat conversation like filling out a form.
That's a great way to think about it. It uses frames and slots. If you ask a system to book a flight, the framework has empty slots for destination, time, and date.
And it relies on natural language understanding to extract those specific semantic values from your messy human sentence.
Right. And a dialogue state tracker maintains the history of the conversation, keeping those slots filled as you change your mind.
There's a fascinating concept here called grounding. In normal conversation, we establish a shared understanding before moving forward. I say something, you nod.
Yeah, the chatbot has to do the same thing. It explicitly says, okay, booking a flight to Paris to ground the transaction before actually charging your credit card.
Grounding prevents catastrophic failures in task execution. It makes sure the system's decision on what action to take next perfectly aligns with the user's intent.
Exactly. But, grounding is tough when the user's input isn't neatly typed text.
Right? Because humans speak. We stutter, we pause, we blend words together. Which brings us to the transition from continuous analog sound waves to discrete tokens.
Handled by automatic speech recognition, or ASR.
Reading through the evolution of ASR, the alignment problem sounds like an absolute nightmare.
Yeah.
How do you map a continuous audio wave to a short word?
Think about the sheer data volume. Audio is often sampled at, say, 16,000 times per second.
Wow.
So a 2-second recording of someone saying a single word generates 32,000 individual data points. Traditional systems try to break this into 3 separate models: acoustic for sounds, lexicon for pronunciation, language for grammar.
But modern neural networks just attempt to learn this end to end.
They do, which brings us to the connectionist temporal classification algorithm, CTC.
Let's visualize how CTC actually works. So we have someone dragging out a word because they're speaking slowly. They say CCAT.
Right.
The neural network is outputting a letter prediction for every tiny time slice of audio. How does CTC collapse that mess into just the 3 letters CAT?
CTC introduces this mathematical innovation, the blank symbol. When the network processes those thousands of audio slices, it outputs a sequence of probabilities. First, the algorithm collapses all consecutive identical characters.
So CCAT just becomes CAT.
Yeah.
But wait, what if the actual word has double letters? Like hello. Wouldn't collapsing consecutive characters turn it into hello?
And that is exactly where the blank token becomes critical. The neural network learns to output the blank token between characters that need to be distinct.
So for hello, it might output EEL blank LO.
Exactly. When the CTC algorithm runs, it collapses the repeats first, getting hey EL blank. Then in the final step, it strips out all the blank tokens, leaving you with the correct spelling, at ELLO.
It elegantly solves the alignment problem without needing manually annotated time boundaries. That is so clever.
And then they usually run a large language model over the final output just to make sure the sequence of words actually obeys the laws of grammar.
Measuring the success with a word error rate. Okay, so we've got these incredible models. They understand context via BERT. They can generate dialogue. They can decode messy audio using CTC.
Yep.
But before we can do any of this, we have to talk about text data processing. Because raw text doesn't just magically turn into machine-readable formats.
Oh, absolutely not. And for students listening, this is a crucial takeaway. Pre-processing is a modeling decision, not just a cleanup task.
Right. The choices you make here shape your downstream performance entirely. You have to tokenize the text, maybe remove stop words or punctuation.
You might use stemming or lemmatization to reduce words to their base forms. Then you have POS tagging, part-of-speech tagging, and named entity recognition, or NER.
And all of that helps build your frequency distributions, your TF-IDF scores, and eventually your dense vectors. But if I try to run a million medical records through all these processing steps and neural models on my laptop, it's going to melt.
Completely. Prototyping locally is entirely different from enterprise deployment. When organizations need to process massive data sets, they turn to frameworks like Spark NLP.
Built on top of Apache Spark, which allows for distributed in-memory computation across massive clusters of machines.
Right.
Looking at the documentation for Spark NLP in the notes, it operates on a very specific, strict pipeline architecture. It uses data frames, which are basically massive distributed tables with named columns.
And the sequence of operations is like a rigid assembly line?
Yeah, you start with raw text, push it into a document assembler, which is mandatory, then maybe a sentence detector, a tokenizer, your embeddings. It goes on and on.
Exactly.
Putting on my pragmatic developer hat for a second, why is it so rigid? What
Yeah.
happens if I'm in a rush and I just, skip the document assembler?
The entire cluster will crash.
Really, just from skipping one step.
Yes, because Spark NLP is fundamentally built on column dependencies. It doesn't just pass raw text from one model to the next, it passes rich annotation objects.
Oh, I see.
When you run raw text through the document assembler, it doesn't just read the string. It wraps it in metadata character offsets, line numbers, document IDs, and outputs it into a specific column.
So if I skip that step,
Your tokenizer, which is next in line, is explicitly programmed to look for a column containing those specific document annotation objects. If you only feed it a raw string, it has no metadata. It throws an error immediately.
so the strictness of the pipeline ensures that when you distribute this computation across 50 servers, the memory footprint and data structure remain perfectly consistent at every stage.
Exactly. You have to transform the data perfectly.
Okay, don't mess with the assembly line order.
Hmm.
Got it. But scaling up to enterprise deployment brings us to the final hurdle in our deep dive today. When these powerful pipelines hit the real world, accuracy on a test data set is no longer enough.
No, not at all. We have to deal with security, vulnerabilities, and ethical guardrails because
Right.
the broader the deployment, the wider the attack surface.
Let's look at adversarial attacks. We all seen the examples in computer vision, right? An attacker changes a single pixel in an image of a stop sign. To a human, it still looks exactly like a stop sign.
But the AI's mathematical weights get confused, and it classifies it as a speed limit sign.
Right. But applying that to NLP seems completely different. Text operates in a discrete space, not a continuous one. If you change a word to trick a spam filter, doesn't it just ruin the grammar and become glaringly obvious to a human reader?
And that is the core difficulty of NLP adversarial attacks. In a continuous space like an image, you can make perturbations so microscopically small that they are invisible to the eye, but mathematically massive to a neural network.
But text is discrete. You can't change a fraction of a word.
Right, you either swap a token or you don't.
So how do you attack an NLP model without sounding like a broken robot?
Attackers use synonym substitution guided by gradient-based optimization. If it's a white box attack, meaning the attacker has access to the model's internal parameters, they calculate which specific words heavily influence the prediction. Then, they search a multi-dimensional embedding space for synonyms that look grammatically identical to a human, but push the model's mathematical decision boundary in the opposite direction.
So like, I thoroughly enjoyed the film might get classified as positive, but swapping thoroughly for a very specific mathematically adversarial synonym might flip the classification to negative,
Exactly, while preserving the human meaning perfectly.
which means developers have to constantly stress test these pipelines. And beyond active attacks, there's the passive nightmare of privacy. These foundational models ingest the entire internet.
They do, and they inevitably absorb highly sensitive data. Personal emails, medical histories, financial records. And because they're generative, they can accidentally regurgitate that data if prompted the right way.
Data leakage.
It's a critical vulnerability. The traditional way to build a model is to centralize your data. You pull everyone's text messages onto one massive server, and you train the neural network there.
But from a privacy standpoint, that's a ticking time bomb. So how do you train, say, a predictive keyboard on my smartphone without sending my private texts to a central server?
You use federated learning. It completely flips the traditional training architecture. Instead of moving the data to the model, you move the model to the data.
Walk me through the mechanics of that.
A central server holds the global foundational model. It sends a copy of that model down to thousands of individual devices, like your smartphone. Your phone trains that local copy using your private text messages.
But my texts never leave the phone.
Never. The phone only calculates the mathematical adjustments, the weight updates needed to improve the model.
So my phone is just sending back the math, not the messages.
Exactly. Thousands of devices send these encrypted weight updates back to the central server. The server averages all those adjustments together, updates the global model, and pushes the new, smarter version back down.
So the central model learns the patterns of human language across millions of users without everyone seeing a single raw text message.
It secures privacy while still capturing the distributional semantics we talked about earlier.
Incredible. So to pull all of this together for the grad students listening, we started by looking at how language models evolved from simple, static dictionaries to the deep, contextual, bidirectional understanding of transformers like BERT.
We broke down how that mathematical understanding gets deployed in the real-world power in chatbots that use dense vector space to retrieve answers or beam search to generate them.
We've explored the sheer mathematical ingenuity required to translate spoken audio into text using algorithms like CTC. and how all of this logic relies on deliberate text preprocessing and strict distributed architectures like Spark NLP pipelines.
And finally, the reality check. The constant battle against adversarial text manipulation and the shift toward privacy-preserving architectures like federated learning.
We've built incredible machinery to navigate the murky, ambiguous waters of human language.
Mhm.
But as we wrap up this deep dive into your course materials, I want to leave you with one final thought to ponder.
What's that?
Well, our open domain chatbots learn how to converse by scraping the sum total of human interaction on the web. They rely on our messy, flawed human data to sound like us.
True.
But as these generative models are deployed at scale, writing articles, generating emails, filling forums, what happens in the near future when the web is completely flooded with AI-generated text? Will the next generation of NLP models end up learning their conversational habits not from humans, but from the synthetic echoes of other machines?
That is a fascinating and slightly terrifying question.
Something to think about before your finals. Keep diving deep.